All right, so for this and the next three questions, I'll do them all together. They are all questions, I think, for the current version. You could be getting it as your question 2 or 3, and many of them involve just simple application of formula, so they should be, you know, easy. But since I haven't done them before, let me do them now. So this is the first question. It asks, what is the strength of the electric field between two large parallel conducting plates separated by this distance, having an electric potential difference between them of this? All right, so we are being given some distance and some voltage difference. And we are being asked for the electric field. And being told or being asked about these quantities, it reminds me of the definition of voltage, which let me write here for reference. The voltage change going from, say, point A to B, and let's make this easy. Let's say electric field is constant. Then that's going to be minus of electric field dot product with the change in the position going from A to B. This is the definition of voltage. And you have one other expression that relates to voltage to other quantities. This is the definition. The other one is more of a convenient relationship to the potential energy. So here we are applying this definition of voltage. It looks like we are not having to deal with any signs or directions. So let me just make things easier for myself. We'll just be dealing with the absolute value. And I think it looks like it's all set up in a way, with the two large parallel conducting plates. So this delta X and the direction of electric field, they should be either parallel or anti-parallel. So this dot product is going to be simple. There won't be any cosine of theta that we have to worry about. So from all that, the expression for the magnitude of the electric field should be left-hand side divided by the delta X from the right-hand side. So change of voltage divided by delta X. So all we have to do is plug in numbers. Let me use Wolfram alpha so that I can save a little bit of busy work in having to convert units. So 5 times 10 to the power of 4 in the E notation. Volts divided by, I'm just going to type in 2 centimeter and rely on Wolfram alpha to do the unit conversion for me and get volts per meter. It's just a simple power of 10. But sometimes people do make mistakes of doing it. So I do think having a tool like Wolfram alpha helps. As long as no. I guess volts per centimeter is a more commonly used unit. So let me say in V over M. So Wolfram alpha will give you some units that it thinks is common. And I guess volts per meter, it's not quite as common as actually kilovolts per centimeter. But anyways, 2.5 times 10 to the 6. So I should be able to enter this as 2.5 times 10 to the power of, that's what E means, 6. So yeah, that's the question. What was the hint gonna say? Yeah, it's basically what I wrote down here. Okay, next question. Let me just erase these. And the formulas I wrote on the right, I'll see if the next question is it. If it does, then I'll use it. If it doesn't, then I'll erase it. Find the maximum potential difference between two parallel conducting plates separated by, okay, I'm still being given some sort of separation. Some delta X of air, given the maximum sustainable electric field strength in air to be... Oh, so I guess here I'm technically being given maximum, but since I'm being asked for maximum, so I'm being given the electric field. So it looks like this definition of voltage will still be useful. I just have to rearrange what I'm... In fact, I don't even have to rearrange anything, because before I had to solve for electric field. Now I'm being given the electric field, being given delta X, and being asked for voltage. I can just do this product. And ignoring the signs, just from the description of the setup, I have some sense my delta X and electric field will be either parallel or anti-parallel. That's all I need. And I don't care about the sign here, so let me do the product. Can I do that? You know, I can even do the product in my head. 3 times 3, that's 9. So 9 times 10 to the 6. So let me turn 3 is 3 times 10 to the minus 2 for in meters. So 9 times 10 to the 6 minus 2 on the top. So it's 9 times 10 to the 4. 9e4. Let's hope that's right. If that's wrong, I'll just go through from alpha. Good. Sometimes mental math can be quicker than having to type in all the numbers, because for simple calculations like that, you know, you can do it much more quickly than having to type it in. So, all right. So that's the second question. The next question, I looked ahead. I think it's gonna be a bit more complicated. Let's see if I still need this. If I still need this, then I'll keep it on screen. But I might have to write down more things. So parallel plates. Now we are being given dimensions of stuff. So that worries me. This is like length on a side. So even though they are not saying square, I'm pretty sure they are talking about square plates. This is what made me think, oh, I'm gonna have to work out some more stuff. Are given equal and opposite charges of magnitude Q. So it's like I have a plate there with a plus Q and another plate down here with minus Q. And they are separated by some distance, let's say D. What is the potential difference between the plates? So I have some formulas memorized, some of which hint might mention. Formula for electric field between two plates. So hint might, it tells you where to go for. I'm pretty sure in this section they derive the formula. So I will just write down the formula that I have memorized in this exact setup, which is, you know, one of the more common situations dealing with the uniform electric field. So electric field in this setup, it's kind of worth memorizing. And the format I have it memorized is as sigma, as in surface charge density of one of the plates. You know, you got two plates divided by epsilon naught. If it had been a single infinite plane, there would have been a factor of 2 here. Because you have two generating electric fields in the same direction, the factor of 2 goes away. Now, this is the way I have it memorized. And I'm trying to use the Coulomb constant more throughout the entire semester. So in terms of Coulomb's constant, this should be rewritten as 4 pi ke sigma. Just have to write this first, because otherwise it's just too many things to do at once in my head to write this down. So it looks like I have to first figure out sigma. So the charge density, it's a density as a density of area. So sigma is the amount of charge divided by area. For square plate, it should be charge divided by L squared. All right, so let's work out the electric field first. I can first see if that makes sense. And once I have the electric field, then I can go through the definition of voltage to figure out the voltage potential difference between the two plates. So for the electric field first, I have charge 6.5 times 10 to the power of minus 9 Coulomb divided by the length on the side squared, 9.1 centimeters squared. Again, I'm not bothering to convert units because Wolfram alpha will do it for me. That's the charge density, sigma. And all I have to do is multiply this to 4 pi Coulomb constant. And I should get something in the volts per length. That is a unit of electric field. So it makes sense. So to get the voltage from the electric field, multiply by the separation or the delta x, that would be 1.5 millimeters. So take all of this, multiply by 1.5 millimeter. Again, not bothering to convert units because Wolfram alpha will do that for me. Just some powers of 10 anyway. Does that, then I have something in volts, 133 volts. And if it didn't give it to me in volts, then I would say in volts. Sometimes when Wolfram alpha doesn't give it in units that you were expecting it could be because you missed something, like, maybe instead of Coulomb constant, you put in electric constant, then your unit will be wonky, it won't come out in volts. So 133. Hopefully that's right. Good. So this question involved a little more step in first having to know the electric field between two conducting plates. And, I think most of you know how I feel about memorizing formulas. And obviously I have this memorized, so it would be hypocritical for me to tell you not to memorize formulas. So I think the way it happens is the kind of formula that's worth memorizing, it should happen naturally. If you are finding yourself spending a lot of time to memorize formulas, what I would say you should spend time on is like learning the problem solving strategies. Like if I didn't have this memorized, I could have derived it from Gauss's law. So, if like my memory failed me, then I would know how to write down Gauss's law, which you should have memorized. So I would start from Gauss's law and know how to apply it to find the electric field here. So, about memorizing formulas, the kind of formulas that are important, that might be worth memorizing, I hope you are spending enough time with the course material that you naturally memorize it. Okay, so let me erase some of these things that are specific to this question and look at the next question and see what stuff on the right I need to keep. So this is the fourth and the last question in this set. Again, of the type of questions that I think are kind of on the easy side, because all you have to do is kind of find one or two right formulas. It says double charged ion. Yeah, I was making mistake about that earlier, so let me make sure that I understand that double charged notation. What it means is the ion has absolute value of its charge is two elementary charges, two electron or two proton charge. Is accelerated to an energy of this. And this electron volt, unit of energy, it's super useful. It actually allows you to do some mental calculation that normally you would need to look up constants in. So, let me finish reading the question and I'll explain how to use that fact. By the electric field between two parallel conducting plates separated by some distance d, what is the electric field strength between the plates? So let me sketch this out and I will tell you why the energy being specified in electron volts means you actually don't have to look up a single formula because that's the usefulness of electron volt unit of energy. So what it's describing is some parallel conducting plates which produces a uniform electric field between them. Let me just have some representation of that. And what the question is describing is a particle of charge 2e that's being accelerated. Maybe this is plus 2e and being accelerated from here to here. It's just going from one of positive potential energy to lower potential energy. So what the question has told you is change of potential energy of 30.6 times 10 to the 3 for kilo electron volt. And the way I like to read the unit of electron volt is like a multiplication between them. So what this is really telling you is the change of potential energy is 30.6 times 10 to the 3 volts, the electric potential, times the amount of charge, one elementary charge. And this is where I'm saying you don't even need to look up any constant, because this change of potential energy, it relates to voltage. It relates to voltage as amount of charge times the voltage change, voltage difference. So when we say this is equal to voltage difference times and the amount of charge, that's where the double charged ion gives that information. The amount of charge you have is 2 times the elementary charge. So if you're thinking of, oh, I need to look up the elementary charge. No, you don't. Cancels out on both sides. So the information the question has given you about potential energy change, it gives you the change of the voltage, the electric potential. It's going to be the numerical value they gave you for electron volts in energy divided by this 2 because of double charged. So we'll have delta V, and we were given the position change delta X. So for the electric field, all I need, again, I'm dealing with absolute values. So for electric field, it should be just delta V divided by delta X. So let me do this calculation in Wolfram above, but without any unit or names for constants, because I don't need any of them. So it'll be 30.6 times 10 to the power of 3 divided by 2. That's my delta V. Divide that by delta X. 1.5 centimeters, I will convert that to meters. So that'll be 0.015. Because so if I'm gonna type in 1.5 centimeters, I needed to put in units for everything else. Here I made the decision to do the unit conversion myself so that I can demonstrate that for this question you actually don't need any constants. So for the answer format, I have some number times 10 to the 5 volt per meter. So let me do it this way. I'm gonna just divide this by 1 times 10 to the 5. Because I suspected that was gonna happen. 10.2. So it's fine. It's mathematically equivalent to that between 1.02 times 10 to the 6. So that's the question. So this is the last of the 4 question set. Again, dealing with mostly definition of voltage. So we used this in every single question, and a couple questions required you to use more knowledge, either of parallel plate setup or I guess of the electron volt units, which I really recommend that you learn, especially those of you who might be physics majors or chemistry majors. This is one non-SI unit that gets used a lot. Like if you take physics 4C, you'll see the electron volts like basically the whole semester, except for when we're dealing with optics, I guess.